Now that we have reviewed transformations of quadratics, I just want to move forward and to explain, I'm going to rewrite the three forms of quadratics that we have. So I'm going to write the first one in factored form. And we know from this that basically how we graph this function is we find our two x-intercepts, and then we take the midpoint of those, we find our vertex, and we can create a graph. We now know that if we have y equals a x minus h squared plus k, what we can do is take our parent function, we can map those 5 points, and using a, h, and k, we can map all of our points using transformations. So what happens when we're given standard form? How do I graph this? Well, if possible, we can always try to factor it, but what we'll notice, and this is Unit 1 of the year, but what we'll notice is that's not always possible, and we're going to talk about this another time. But what we can always do, no matter what, is we can always put standard form, which is this form, into vertex form. And I'm going to show you how to do that. The process is called completing the square. So let's get to it. And actually, we've seen this before. We did this in our circles unit. So basically, what I want to do, if I'm given a quadratic, and I've typed this all out for you on the side here, but you can just follow my instruction. What we want to do is we want to get this, remember, in the form y equals a x minus h squared plus k. So the first thing we do, as outlined right here, is we're going to factor out a of the x terms. What do I mean by the x terms? I mean these two terms right here. So what I'm going to do is I'm going to factor out the a from those two terms. Now the key thing here is that what I have in front of my x squared is a 1. So no matter what, within this bracket, we want to make the coefficient of x squared 1. Okay, so I'm just copy and pasting the rest. So you guys agree with me that we can see how these two things are beginning to look like each other. Okay, now what do I do next? Well, what we're actually going to do is we want to make the inside a perfect square trinomial, and we've already done this. So if you recall, what we did is we sort of left some space here, and we said, well, I need to add two terms that sum to 0, but that will make this thing a perfect square. So what we did is we took our coefficient of x and we divided it by 2, and then we squared the result, right? So what I'm going to do is add 3 squared, but then I need to subtract 3 squared because I know that this thing has to have a sum of 0. What I'm going to do in my next step, just to make it a bit easier to look at, is I'm going to write these 3 terms as plus 9 minus 9. Okay, and we can sort of see how this is going to shape up. Now, before we do anything, I have to remind you that we're not going to expand, but if I were to expand, okay, and if I wanted to, in fact, get rid of this bracket, I would have to distribute the 3 to every term within this bracket. I don't want to distribute, though, at least not to the whole thing. But what I need to do is recognize that the thing here that makes my perfect square is actually these 3 terms together. So I don't have any use for this guy inside my bracket. So what I'm going to do is I'm going to take it out of the bracket. But as you can imagine, as I take the -9 out of the bracket, I have to make sure that it's being multiplied by 3. Beware of the sign, so make sure that you're multiplying by -9 plus 20. We're almost there, guys. So we're going to do a lot of steps right now at once. So we know that this factors. We know that this becomes x plus 3 squared. We also know that this is subtract 27 plus 20. So my final answer is going to be -7. Okay, so here I go with my final answer. So at the end, we do have y equals ax minus h squared plus k. And further to that, I can graph this now. So let's go ahead and state the transformations. We know that a is 3. We know that h is -3. And we know that k is -7. So I know my vertex is at -3, -7. I know my axis of symmetry is -3. And I know my range is -7 to infinity. Just gonna move this out of the way. Okay, so in order to graph this, what I want to do is, if you recall from last class, I'm going to map all the points x, y to my new points x prime, y prime. And the way I do that is by using the special formula x prime equals x plus h, y prime equals ay plus k. The way I like to do this is in a chart. That's my preferred method, but you guys can just write them out as separate coordinates if you want. So what I like to do is I like to start my chart exactly the same every time. Okay, and that's by putting in 5 important points of the parent function. Okay, so we can always start there. So, and then what I like to do is I like to build out the table horizontally and vertically. What I mean by that is obviously horizontal changes have to do with x and vertical changes have to do with y. So in order to get my x prime values, I need to take my x values and I need to subtract 3 because that's what h is. Okay, so I'm going to subtract 3 from all these values. And I'm going to do a similar thing on the other side, but I'm actually going to do it in 2 columns. So first, I'm going to multiply each, let's actually write the a value in. I'm going to multiply each of the y values by, and we said that a is 3y. All right, so I get 12, 3, 0, 3, 12. And then in my last step, so from here to here, I multiplied by 3. From here to here, I'm going to throw in the subtraction of 7. So I'm going to take these values and subtract 7. All right, so now I can see my mapped values just by reading the outer columns. So this will be my y value. This will be my x value. Okay, so let's graph it. Comments, we can definitely see that this is 3 times stretched from the parent function. We can see that the vertex is -3, -7, which we knew before we drew the graph. And we also can see that the range is -7 to infinity. So what I'd like you to do now is I want you to try the next 2 questions on your own and check against my answers at the end of this video.